Hello, everyone. Welcome to the lecture on plotting and charts. So we're going to cover quite a bit of stuff, including like more features of the IDE and how to read documentation today. So this is definitely a good lecture to watch for that kind of stuff. And then all the nitty gritty plotting and chart details are in chapter 3 of your book, which is a really good reference. I would skim through that and then just so you know where everything is and what's possible, and then reference it as you work through the lab. So first, we're going to create a chart of the sine function using, well, actually, chart of, sure, we'll do sine function with list comprehensions. So we need some X and Y values to create a chart. So we'll say our X is equal to, and then list comprehension, X for X in range. And see range, we can do a little command I on Mac. It should tell you what else under the help thing if you're not on a Mac. Because we want this to go from 0 to 2 pi, so we get one full cycle of the sine. And we want to have a lot of steps, so it looks like a smooth sine. So this says return an object that produces a sequence of integers from start to stop. So since these are integers, it won't, let's say we want 100 steps, and we'll do X divided by 100 times 2 times math.pi. So we'll have to import math. We'll also have to import our plotting library. So import from matplotlib.pyplot, import, or I always forget what this one's supposed to be. It's import matplotlib.pyplot as PLT. So PLT is saying we're renaming this module to PLT so we can use it without having to write all this stuff here. We can also import, let's see what the other one is, numpy as NP, and then we'll use those down here. So now we've got our math. What we're saying is in this list comprehension for X in range 100, so we're going to make a list of 100 elements long. We're going to say divide X by 100. So this will go from 0 when X is 0, all the way up to 1 when X is 100, 100 divided by 100, times 2 times math.pi. So this is just a complicated way of saying we want 100 numbers between 0 and 2 pi. So we'll create our Y. Y is going to be sine of X for X in, sine of element for element in X. And define name sine, math.sine. There we go. So this is going to create a new list that's the sine of every element in X. So you can see list comprehensions, not bad, but not super readable for this. It's not incredibly obvious what's going on. But then to create our actual plot, we'll say plot.plot X, Y, and then plot.show to display it. So when we run this, it'll pop up over here under plots. And we can see here's our sine, default color is blue. There's our sine function. Now we can create another one. Well, first let's go over the easier way to do this step. So rather than messing around with the list comprehensions, we could equivalently say X is equal to np.linspace. And linspace, let's look at the help docs. So this function returns evenly spaced numbers over a specified interval. So specified interval looks like we have start first, so we'll start at 0. and then stop will go up to 2 pi. It's 2 times math.pi. And then how many we want, the numbers. Let's say we want 100. So this line now for x is exactly equivalent to this line. So we'll just comment this one out. Then for y, rather than using list comprehension, we could use NumPy's version of the math sign. So y is equal to np dot sign of x. You see it's a lot more simple, a lot more readable. The sign function in the NumPy version takes in an array and then returns an array. Or we'll get more into the details later. It's not technically an array, but it is an iteratable and it behaves like an array. So now if we run this again, jump over to our plots, we can see we got 2 more or less identical plots. The difference, actually, somewhat important difference. This one, the first one, range does not include the last element. So this goes up to 99. So the most we get is 99 out of 100 times 2 pi. So not quite up to 2 pi. So this doesn't get all the way back to 0. Versus this linspace is inclusive. So this goes from 0 all the way up to and including 2 pi. And that's why this one goes just a little bit farther and gets all the way up. If we want to make them truly equivalent, we could make this 99. We've got that and that. Nope, not 99. This would be 100 and this would be 99 out of 100 times that. There we go. So now we can see these two are identical. But that's not what we want. That was just a little bit of a bug in the first example. Sweet. Now this is all cleaned up. If we wanted to add another line to our graph, we could add y2. It's equal to np.sign of, let's say, we want this to have twice the frequency, so we'll do 2x. Then we make a new line, plot.plot x, y2. So the first plot.plot makes the line of x and y. Second one makes the line of x and y2. And this is all covered in the chapter 3 as well. So we run this, we can see our 2 lines and it automatically differentiated the color for us. That's really helpful. But if this weren't enough, we could add some line options. So let's say line style is equal to, we'll make this one a dotted line. And then just to show it off, we'll make this one a dashed line. So now we can see they're very, very different. A quick aside is like, how did I know this is line style? Short answer, it's in the book. Longer answer, if you want to see all the options for plot.plot, we could jump on over to Google and look up matplotlib pyplot.plot, and then we could read the documentation on matplotlib. So this can be a little bit intimidating to look at first. There's like so much stuff going on, but it's really just helpful examples. And we know we want to change, let's say we want to change the color. So just how I do this is I search for something like color and see, okay, here, the format for basic formatting, that's seems like when we do it over here, it looks like they're using color equals green. So just copy that and throw it into our code and see how that works. Sweet, now we've got a green one and a blue one. Let's say we want them both to be green because we want it to be confusing. Now we can see they're both green. So quick aside on these are what's called keyword arguments. So these first arguments are called positional arguments because their position determines what they stand for. So this first one, x and y, or x and y2, stand for X and Y here. And those are just based off of their position. So if we were to switch these, let's say we graph Y and X and comment this one out. Now we get this crazy graph that has our Y values as the X axis, and then our X values as the Y axis. So now see the Y goes from 0 to 2 pi and X goes from -1 to 1. The function here doesn't really care that this is called Y and this is called X. It just says, take whatever's the first position and assign it to, let's see if we can open up the help window. Whatever's in the first position, nope, not helpful. Sometimes you get a help window like this that doesn't really show us anything, no further documentation. So it says take whatever's the first argument, put that in X, take whatever's the second, put it in Y. These keyword arguments, on the other hand, say take this and set it, the value of line style equal to that. Set color equal to green. So the position of the keyword arguments doesn't matter at all, and we can switch them around, put them wherever we want. The only condition is that once you switch to keyword arguments, you have to remain at keyword arguments. You couldn't put a keyword argument in front of positional arguments, because then Python doesn't know which position the arguments are supposed to be in. So if we even try to run this, it'll give us an error. Yeah, positional argument follows keyword argument. So if you ever see this error, it's saying that you've got some of these equals arguments before your positional arguments. Change that back to normal. Awesome. Sweet. So that is how you go over, or how you create graphs and charts in Python, and all the details are in the book, plus a little bit on how to read documentation and just generally use your IDE.